Hello again. Uh, so this is a research talk. If you've understood my previous lectures, you might be able to understand the gist of what I'm talking about, but I'm afraid this will be more advanced than those, considerably more so, right? So this is about numerical criteria for generalized Monge Ampere equations on projective manifolds. It's a recent result of ours. With myself and Ved Datar from my SC. Alright, so let's get down to the bottom line of this talk, bottom line of our paper, if you will. So at a very high level, not getting into details, we proved that certain partial differential equations, the so-called generalized Monge Ampere equations, can be solved on compact complex manifolds which are projective, in the sense that they can be embedded in projective space if and only if certain integrals over all subvarieties are positive, meaning that these PDE cannot always be solved. Okay, there's an obstruction there. They can be solved if and only if certain integrals over all subvarieties are positive. This is it's a formidable condition to check. The reason is we have to look at all possible subvarieties, and there are infinitely many of them, right? So it's not immediately obvious as to how you would check it. But anyway, so our theorems can be used to recover existing results on this subject. It's not like ours is the first. So there's the J equation, which is a special case of the generalized Monge Ampere equations. This J equation is interesting for various reasons, and similar results, that is numerical criteria implying that the J equation can be solved, were so originally Collins and Sekilahidi, they proved it in the Toric case. Then Gauchen, relatively recently, last year, in a spectacular paper, he proved it for the J equation in the Köyü case. Okay, not exactly the result we proved, slightly weaker, but nonetheless. Okay, there are other equations. Other than the J equation, there's a so-called deformed Hermitian-Yang-Mills equation motivated from string theory. For the deformed Hermitian-Yang-Mills equation as well, Gauchen proved a similar result, that is, this equation can be solved if and only if certain integrals over subvarieties are positive. Actually, for the deformed Hermitian-Yang-Mills equation, for very special cases, even I proved it earlier on toric varieties. But Gauchen's is, first of all, in a far more general setting, and the proof is also very ingenious. Okay. All right. So our theorems can be used to recover certain results, more or less. Except the deformed Hermitian-Yang-Mills equation, we cannot recover Gauchen's results in their full generality. We can only recover special cases of them, but nonetheless, okay. And our theorems also improve upon the existing results in certain cases. Yeah, so they're also new in certain cases. So as a corollary of our work, we prove a conjecture of Sekilahidi, Gabor-Sekilahidi, which is itself a generalization of an earlier conjecture with Lejmi in the projective case. Yeah? Right. So these numerical criteria, that is, integrals over certain subvarieties, are positive. If you're familiar with algebraic geometry, they're analogues of the Nakai-Moitzeschon criteria. Okay, so this is the bottom line, right? So without further ado, let's get down to the brass tacks. So here is one of our theorems. So suppose you have a compact projective manifold, omega naught and chi are Kähler forms on it. Yeah. So suppose Ck are constants, they're all non-negative, at least one of them is positive. F is a smooth function If f is greater than or equal to 0, then that's allowed. But f is also allowed to be slightly negative. And how negative it's allowed to be depends on the coefficient ck as well as the integral. I'm so sorry, there's a typographical error there. It's the integral of omega naught raised to n over the integral of chi raised to n over m. Okay. Anyway, some technicalities. The following are equivalent. The first thing is the generalized Monge Ampere equation has a unique smooth solution. So what is this equation? So we know what the Monge Ampere equation is, right? What is it? It's omega raised to n is f times chi raised to n, where f is positive, right? That's the Calabi volume conjecture. Yeah. The reason I call it the generalized Monge Ampere equation is it's not just, so locally what is the Monge Ampere equation? Omega raised to n is simply, roughly speaking, the determinant of the Hessian, right? And the right hand side for the Monge Ampere equation would be a given volume form. But here it's the determinant of the Hessian equals some combination of the other symmetric polynomials plus a volume form. Not necessarily a volume form, but something akin to that. By the way, there's also one more assumption, it's a technical one, two more assumptions. One is the integral on both sides has to be equal. Okay, the integrals have to be equal, and the integral of f chi raised to n has to be non-negative. Okay, these are technical assumptions. I'm very sorry I forgot to put them in here. But nonetheless, this particular PDE has a unique smooth solution in a given Kähler class. Okay. The second equivalent condition is there exists a metric in the scalar class satisfying a certain inequality, the so-called cone condition. Okay. Now this should already raise eyebrows, right? What about the usual Monge Ampere equation? Do we have a cone condition for that? Well, for the usual Monge Ampere equation, this cone condition would simply boil down to there exists an omega so that omega raised to n minus 1 is positive. Of course, omega naught itself satisfies it by virtue of being a Kähler metric. Yeah, so it's not so shocking. Yeah. The problem with this cone condition is it is as hard to find a metric satisfying this inequality as it is to actually solve the equation itself. Right? How would you find such a metric? It's not at all straightforward. Yeah. So how would you verify that this equation can be solved? I mean, so we need a better criterion, something that is a tad bit easier to check. And that criterion is as follows. If you take any subvariety, it can be smooth, it can be singular, a certain integral is positive. Yeah. But what does it mean for an integral of a differential form on a singular variety to be even defined? What it means is you integrate over the smooth part of it. And if you read Griffiths and Harris well enough, you will see that that's good enough to make sense of it. Stokes' theorem, etc. hold. Yeah. So if you can verify this numerical criterion, namely the integrals over subvarieties of these things are positive, then this PDE has a solution. Granted, it's not easy to verify this because you're taking all possible subvarieties. Yeah. But I must say that we also proved another theorem in our paper where some symmetry is allowed. For instance, if M is a toric variety. Now what is a toric variety? CPN, for example, is a toric variety because S1 raised to n acts on it. Yeah. How does S1 act on, say, CP1? You just take one of the homogeneous coordinates and multiply it by e raised to I theta. How does it act on CPN? You just multiply the last few by e raised to I theta I. Okay. So a toric variety is something on which not just S1. Basically, a toric variety is a compact manifold that contains C star raised to n as an open dense subset, along with certain other conditions. But anyway, if you don't know what a toric variety is, anyway, it's a manifold with a lot of symmetry. Yeah. So there are toric subvarieties, namely subvarieties with a lot of symmetry, and happily enough they're only finitely many in number. So it's not very hard to check this, because you need to only make sure that finitely many integrals are positive. Yeah. So for toric varieties, for instance, we have a version of our theorem. Okay. And we have it in slightly more generality than just toric varieties, but yeah, for sure for toric varieties it works. Yeah. So this is our main result, right? Yeah. All right. So now let us now let's actually go into the background of the story and see why you should care about these things and so on. Okay. Now that we've seen what our main result is. So all right. So here is a seemingly silly question. If I give you a Dirham cohomology class of type 1, how do you know it's a Kähler class? Meaning, how do you know if there's a Kähler form in it, other than explicitly producing one, right? There are obvious necessary conditions. For instance, the integral of omega raised to n, which only depends on the cohomology class, by the way, it has to be positive, right? So there are obvious necessary conditions, but are they sufficient? So the Nakai-Moitzeschon criterion for projective manifolds, it's an algebro-geometric criterion. And in the Kähler case, the Demaille-Pon criterion. So the most general criterion is the Demaille-Pon criterion. The Demaille-Pon criterion tells us how we can answer this question. So omega is a Kähler class, meaning it has a Kähler metric, if and only if for every subvariety the integral of omega raised to p is positive. In other words, the volume of every subvariety is positive. Right? And it's an obvious necessary condition. The miracle is that it's sufficient. Yeah. So just for technical reasons, when I say a uniform Demaille-Pon criterion, what I mean is if you give me a fixed Kähler metric, then integral of omega raised to p is not only positive, it's greater than or equal to epsilon times the integral of alpha raised to p, where epsilon doesn't depend on v. Obviously, if it depends on v, this is a triviality. Yeah, and epsilon is positive, of course. And I'm just making a definition here. Okay. All right. So the Demaille-Pon method of proving this Demaille-Pon criterion is you take omega plus t alpha for large t. Obviously, for large enough t, this is a Kähler metric. It's a Kähler class, right? The idea is to use the method of continuity. For large t, this is a Kähler class. We want to show that at t equals 0, also it's a Kähler class. So you show that the set of t for which it's a Kähler class is both open and closed. Yeah? It's obviously open. I mean, if omega plus t alpha is a Kähler metric, obviously if you perturb t a little bit, it'll still be a Kähler metric. The point is whether it's closed. Namely, for instance, if t goes to t naught, and omega plus t alpha for t larger than t naught, these are all Kähler classes, do we know that even at t equals t naught, omega plus t naught alpha is a Kähler class? Okay, that's the key question, right? So this is the basic strategy, but of course, that's not saying much. I mean, you can call anything a basic strategy, right? The devil lies in the details, if you will. Yeah. Okay. One key point in this Demaille-Pon method is the ability to solve the Monge Ampere equation. Sorry, not on this subset. It's the ability to solve it on all of m cross m, except you want something special to happen on the diagonal. Okay, what do I mean by that? I'll come to it a little later. Okay, so this is a very key feature of the Demaille-Pon method. Why am I emphasizing this so much? Because this is a very ingenious point. It might seem simple in hindsight, but you see, if you take a general Kähler manifold, you may not even have a subvariety, right? In that case, every class is a Kähler class according to the Demaille-Pon criterion. Yeah, because this is vacuously true. So how would you use it to prove the result? How would you use it if you don't have any subvarieties, right? It sounds a little difficult. So it seems like if you can manufacture a subvariety of something from somewhere, there might be some hope. I mean, Demaipon, one of their insights is if you take M cross M, it always has a subvariety delta. I do not mean to say that you test this against this delta. No, not at all. It's much more complicated than that. But still, this is itself a new idea. Okay. To give away the suspense, in our proof, we do not use the diagonal at all. This is one of our innovations, if you will. Okay. But as a consequence, we have to work in the projective case. Okay, because projective varieties have lots of subvarieties. That's the key point. Okay. All right. So that's that. Now I mentioned the so-called J equation in my first slide. I mumbled a few words about it. Let's go into that in more detail. So as I mentioned in my lectures, the constant scalar curvature Kähler problem is still unsolved in its full level of generality. Yeah. So we don't know when CSCK metrics exist and when they don't. One possible approach, the CSCK problem, is after all a partial differential equation. One approach to studying PDE is calculus of variations. That is, you have an energy, and hopefully if you minimize it, the minimum solves the desired PDE. There is an energy called the K energy that's known to satisfy this property in the sense that if you have a smooth minimizer of the K energy, you do have a solution to the CSCK problem. Okay. So the K energy can be written in as a sum of three terms. This E is what we can call the entropy term. Yeah. And you have the I and J terms. Yeah. So assume that C1 of M is less than 0. Recall that in the case of the Kähler-Einstein Calabi conjecture, C1 being negative is the quote-unquote easy case, right? But if C1 is negative and you want to solve the CSCK problem on some other Kähler class, not the usual Kähler class for the Kähler-Einstein metrics, then even then it's not clear as to how one would do it. Okay, so just because I'm assuming C1 is negative does not automatically trivialize the problem. So it's known that I plus j is convex along weak geodesics. Well, what does that mean? It's a long story, but the bottom line is if you take the space of all Kähler metrics, that's like an infinite dimensional manifold. It has an infinite dimensional Riemannian metric. You can define infinite dimensional geodesics. Not quite, I'm lying a little bit here. That's why the adjective weak geodesics, but let's forget such technicalities. So you have infinite dimensional geodesics. And one knows that I plus j is convex along these, right? One also knows that the entropy term is bounded below. Okay, so k is bounded below by I plus j, which is a convex function along these geodesics. So if a convex function has a critical point, then it is bounded below, right? Because that will be a global minimum. So this crucial observation, the ability to write the K energy this way, and this observation, the spectacularly brilliant observation, was due to Shushong Chen. Yeah. So by the way, Shushong Chen's paper, it's I think called on a lower bound of the Mabuchi energy and its application. It's a very nicely written paper. I invite you to read it. It's an IMR, old paper. So the point is, a functional having a critical point means that a PDE has a solution. These two are equivalent. That PDE can be generalized to the so-called J equation. This was originally introduced by Donaldson and then Shushang Chen studied it further in that paper I mentioned. The J equation is omega raised to n, right, just like the Monge Ampere equation, equals not something that's given, but it's instead omega raised to n minus 1 times chi, where chi is another fixed scalar metric. So you want to find a scalar metric omega given a fixed scalar metric chi and a scalar class omega of omega satisfying this equation. Okay, so what does it look like locally? Suppose you choose coordinates at a point such that chi is the identity matrix and omega is diagonal with eigenvalues lambda I, then this equation is simply sum of 1 over lambda I equals 1 at that point. Contrasted with the Monge Ampere equation, which is the product of all the lambda I is a given quantity. Here the sum of 1 over lambda I is 1. Yeah? Alright. So unfortunately, this equation does not always have a solution. Okay? Why? Suppose it did have a solution omega. It's not very hard to prove. In fact, let's do the proof very quickly. If 1 equals sum over I of 1 over lambda I, then 1 is strictly larger than sum over 1 over lambda I where I miss one of the lambdas. Namely, 1 is larger than 1 over lambda 1 plus 1 over lambda 2 plus so on until 1 over lambda n minus 1, for instance. Right? So that's a necessary condition. Meaning, if I have a solution to this equation, there better exists a metric in the scalar class satisfying this necessary condition. This necessary condition is called the cone condition, and it can be written in the language of forms in this way. But this is exactly equivalent to writing it in the simpler way I just mentioned. Okay? It's just that 1 is larger than the sum of 1 over lambda I if you omit one of the lambda i's. Of course, if you omit 2 of the lambda i's, that's also still true, and so on. Okay. So, assuming this cone condition, assuming this necessary condition, Shushang Chen observed that in 2 dimensions, this equation can be related to the usual Monge Ampere equation that we all know and love and know how to solve. Jian Song and Ben Weinkoff proved that this J equation has solutions for all dimensions, assuming the cone condition. And they proved something even better. They proved that the K energy is also proper. As in, assuming the cone condition, we have a hope to find CSCK metrics. Okay? We have a hope, mind you, that it's not immediately clear, because at best, with some effort, properness would imply that there is a weak solution to the CSCK problem. To prove that there's a smooth solution, one needs to know some strong PDE estimates, which were provided by Shushang Chen and Cheng. Only relatively recently, I believe, some of the lectures in this workshop cover Chen and Cheng's work. Right? So that is the crucial importance of the J equation, that using it we can produce lots of examples of CSCK metrics. Okay? And therein lies the importance of the cone condition. So we should be able to check the cone condition efficiently, or else all of this is pointless. Right? And unfortunately, the cone condition is difficult to check. It's as hard to check it as it is to solve the J equation itself. Right? Alright. As I said, the cone condition is hard to check. So Lejmi and Sekilhidi conjectured that a numerical criterion, just like the Demai and Pon or the Nakai-Moitzischon criterion, is enough. Okay. Why is this? Why is that a necessary condition, by the way? If you go back here, so what is the cone condition? 1 is larger than sum of 1 over lambda I for if you drop one of the lambdas, right? So if you drop 2 of the lambdas, that's still true. If you drop 3 of the lambdas, that's still true, and so on. Right? So the cone condition implies lots of such cone type conditions. All of them can be written in terms of forms akin to this. Right? So if you integrate such things over subvarieties of appropriate dimensions, you get positive numbers. So the fact that it's necessary, this integral condition, is not very hard. The question is whether it's sufficient. Okay? Lejmi and Sekilhidi provided some evidence that this is sufficient. Okay? So Tristan Collins and Gabor Sekilhidi proved this conjecture in the toric case, meaning if you have a toric variety and chi is a toric variety is simply a very symmetric manifold. If chi is also equally symmetric, then for all symmetric varieties, which are finitely many in number, this better be positive. So that's very reassuring, because it's not very hard to check. You only need to make sure finitely many integrals are positive. Okay? So this was open, the general case, till last year. Gao Chen proved it under the assumption of uniform positivity, meaning that it's not just that this is positive, there's an epsilon, so that this is larger than epsilon times omega raised to n minus p integral over v, where that epsilon doesn't depend on v. Okay? Under this somewhat mild strengthening of the hypothesis, so this result is slightly weaker than the Sekilhidi conjecture. Okay, so Gaussian proved this in the Kähler case, no less. Right? It's a spectacular paper. Okay, it's very impressive and very technical. Yeah. All right. Unfortunately, uniform positivity is also hard to check. I mean, checking this is hard enough, but checking uniform positivity is even harder. Okay. So we want to get rid of the adjective uniform. I'm so sorry. Maybe the word stability should have been positivity. Please, I mean, it's not quite a typo. You can also call it stability, but please neglect this word. What we did, our theorem generalizes Gaussian's work by removing the adjective uniform, but at the cost of proving it only in the projective case, not in the general Kähler case. Okay, so that's one of our contributions. The other contribution that we made is, notice that even with this result of ours or with Gaussian's result, you can't really recover Collins and Sekilhidi's result, because ideally what you would want is, if a group acts on the manifold, you would want to test this numerical criterion on only very symmetric subvarieties, right? You don't want to test it on all subvarieties if the manifold is sufficiently symmetric. So actually our theorem also works for an equivariant version, namely if a group of a certain type acts on a manifold, you just need to test against symmetric subvarieties, provided you assume uniform positivity. Okay, so it's like Gaussian's result, but an equivariant version of it in the projective case. If you don't want uniform positivity, you have to test it on all subvarieties. Honestly, we believe it's just a technicality. We should be able to prove this sort of a result even without uniform positivity, but so far we haven't been able to prove it. Okay? All right. So let's look at another equation, which special cases of which are also covered by our theorem. It's the deformed Hermitian-Yang-Mills equation. So Jacob and Yao introduced this equation. And the equation, whatever it is, it's a partial differential equation. What do you solve for? You solve for a metric on a holomorphic line bundle whose curvature satisfies a nice equation. Okay, that's what this equation is about. So this equation is motivated from mirror symmetry in string theory. It's a long story. Several people have worked on it. and several people have worked on the deformed Hermitian-Yang-Mills equation also. I'm sorry, I'm not citing everyone's work in this talk. There's not enough space on my slides to do so. Please look at our paper. We've cited everyone's work. So this is a very active area of research. Several people have been working on it. So Jacob and Yau introduced this equation. The idea is to solve for a metric h whose curvature theta satisfies some polynomial equation. Omega is a given Kähler form. Theta hat here, I mean you see tan theta hat, that's a constant. Okay, it's a constant designed so that the integrals on both sides are equal. And this theta hat is called the phase angle. Okay. So Collins, Jacob and Yau proved existence for this equation, assuming a cone style condition. Okay. Except their result doesn't work for all phase angles. Tan theta hat should not be too negative. Yeah. So that's their result. So we conject, actually Jacob and Yau conjectured, or maybe it was Collins, Jacob and Yau, I don't remember. So they conjectured that a numerical criterion is enough, that you don't need to assume a full cone type condition. Okay. So firstly, forget the numerical criterion. Even assuming a cone condition, existence is not fully known, right? When Collins, Jacob and Yau proved existence, assuming tan theta hat is not too negative. So I managed to prove that for all tan theta hat, even if it's very negative, assuming a cone condition, you have existence, but for dimension 3. For dimension 2, it's not very hard, as Jacob and Yau observed, it reduces to the Monge Ampere equation. For dimension 3, I proved it. Then Gauchen recently proved existence for all n, and not just assuming a cone condition, assuming a uniform numerical criterion, no less. Okay, so that's a very impressive paper again. Again, the problem, not quite a problem, it's a very interesting result and quite ingenious. The only small hiccup is it assumes the uniform version of the numerical criterion. Okay, right. And just like Collins and Sekelihiiri proved for the J equation, I proved existence on toric varieties, but for very, very special phase angles, not as general as Collins, Jacob and Yau for sure. For special phase angles, assuming a numerical criterion for toric subvarieties. Yeah? Alright. So our current results, they cover my previous existence result. They also cover Gauchen's result for special phase angles, but we allow just the usual numerical criterion. We don't need a uniform one. Okay. So for very special phase angles, we have an improved result. Okay, so we proved the conjecture of Jacob and Yau and for those special phase angles. Alright, so more equations. So generalizing the J equation, what is the J equation? The J equation is sum of 1 over lambda I equals 1. That is the trace of the inverse of the Hessian matrix equals 1. You can ask whether other symmetric polynomials of the inverse of the Hessian matrix being equal to 1 can be solved. Those are called the inverse Hessian equations, and indeed they can be solved assuming the cone condition. This was first proved by Fang, Lai and Ma. So I introduced the generalized Monge Ampere equation after that, and I proved very few results. The point is, the general existence result for the generalized Monge Ampere equation, assuming the cone condition, was proved by Wei-Sun. You can write other equations too, the so-called Hessian equations. That is, what is the Monge Ampere equation? It is the determinant of the Hessian equals a given thing. What's the Laplace equation? It's the trace of the Hessian equals given. So you can ask in between, that is the kth symmetric polynomial of the Hessian being given, right? Those are called the Hessian equations. Those have also been studied assuming the cone condition. Yeah? So lots of people studied these, by the way. Watsky started it, then Coulomb and lots of others. I'm sorry, I didn't cite everyone, but all the citations are there in our paper with Ved. So Gabor Sekelichidi, he proved existence for a very general class of equations that includes the inverse Hessian equations, the Monge Ampere equation, and the Hessian equations, assuming the cone condition. Yeah. In the same paper, he conjectured that to prove his result, numerical criteria are enough instead of the cone condition. From our paper, you can prove Sekelichidi's conjecture for the special case of inverse Hessian equations on projective manifolds. Yeah. So all right. So that's that about background, existing results, and how our results tie in with the existing results, why you should care about these things, and so on. By the way, in case you're wondering why you need to care about, okay, see, I hope you're convinced that the J equation is something you need to care about because it comes from CSEK metrics. Deformed Hermitian-Yang-Mills, sure, you need to care about that, it comes from physics. Why should you care about, say, for instance, the Hessian equations or the other inverse Hessian equations? I must confess I don't really have a good reason for caring about the other inverse Hessian equations a priori, except that the techniques are the real lights at the end of the tunnels here. Okay, the techniques are what are important here. So for instance, the Hessian equations per se, they're not, you don't have to care about them, but the techniques of Watsky, Coulomb, etc. for the Hessian equations are useful in studying other equations of a similar nature coming from physics, the so-called Fuyao system and so on and so forth, and other equations coming from geometry as well, studied by Valentino Tosati, Ben Wynkow, etc. Okay, Duong Fong, etc. Okay. So that's the reason. So these equations, directly you may not have to care about them, but indirectly they may be helpful in studying related equations. They may be toy models of related equations. Yeah? Alright. So let me spend some time explaining the very high level overview of Gaussian's proof, and then I'll explain our proof, a very high level overview of our proof. So basically, Gaussian's proof was inspired by Demy and Pond's strategy. Okay. But just because it's inspired by Demy and Pond's strategy does not make it any less ingenious. Even if I tell you Demy and Pond's strategy, it's not immediately obvious how you would come up with a strategy to study Sekelichidi's conjecture, right? I mean, Demy and Pond's paper was written a long time ago. Okay, so it's a very impressive piece of work. By the way, a scandalous remark, many people think Gaussian's work is wrong, but actually they are wrong. Gaussian's work is perfectly correct. At least we have read through his paper very carefully because we needed to use his strategy, right? So Gaussian's work is perfectly correct. So the proof, just like in Demy and Pond, is induction on the dimension of M. So if the dimension of M is 1, that is, we are dealing with Riemann surfaces, proving these theorems is not rocket science. Okay? I invite you to try to do it on your own. Okay? It's very straightforward. So first, what Gaussian does is that just like Demy and Pond, if you've read Demy and Pond's paper, he proves that in a slightly smaller cohomology class, meaning if you subtract a little bit of a Kähler form, in this Kähler class there exists a current. Now if you don't know what a current is, you'll have to look it up, but basically a current is a form with distributional coefficients. Yeah. So there's a current satisfying the cone condition. Now this is a very dangerous thing to do, because what is the cone condition? Let's go back to the cone condition. What's the cone condition in the language of forms? It's this. To even write down the cone condition, you need to be able to multiply forms. Now already there's a very big problem, right? How the hell do you multiply distributions? You can't always multiply them. Now this is one of Gaussian's spectacularly ingenious insights. He does not define the multiplication of a current with itself. He does not need that to define the cone condition. He says that a cone condition is met. Okay, roughly speaking, if you take a coordinate chart and you convolve theta, then you get a smooth form. That satisfies the cone condition in a certain sense. Okay, I'm still not being completely honest. There are still some technicalities, but roughly this is Gaussian's idea. He does not have to define what it means for the current to be multiplied with itself. You don't need that to define the cone condition. This is one of his key contributions. I believe that is why some people are uncomfortable with his paper, because it's very hard to define these wedge products and they don't always exist and so on. But you don't need that for Gaussian's strategy. Okay, I have to emphasize this. So just like Demy and Pon, Gaussian also needed to go to M cross M and look at the diagonal. Okay, he had to prove concentration of mass. So roughly the idea is you study the J equation on M cross M, a family of J equations depending on a parameter T. As T goes to 0, you prove that the solutions converge to a current which puts some mass on the diagonal, meaning the current is larger than some positive number times the integration current over the diagonal. Okay. Now this sort of a thing was done in Demy and Pon as well, but for the J equation, it's actually it's not at all straightforward. Okay. So that is one of the things of Gaussian. Okay, there are some tricks involved here. So, all right. So great. You have a current in a cohomology class satisfying the cone condition. Unfortunately, you need a smooth form that does it, not just a current, right? So what's the difference between a current and a smooth form? The current is singular. So you can actually quantify how singular this current is. The bad set, namely, how badly behaved a current at a point is measured by its Lelong number. It tells you the logarithmic singularities in the potential of the current. Thanks to Su, this bad set of high Lelong number is a proper analytic subset, meaning that it's a set of measure 0, for instance, in M. Okay. So in a neighborhood of this bad set, one can use the induction hypothesis to show that there is a metric omega prime, a smooth metric, satisfying the cone condition. So in other words, we sort of solve the problem, but in a neighborhood of the bad set, right? If this bad set was simply a smooth submanifold, this is not rocket science. Why? You simply add a large multiple of del bar of the distance squared to this bad set, and that will satisfy the cone condition in a neighborhood. The tricky part lies in doing the same when you have a singular object. If the bad set is a union of singular subvarieties, or even a union of smooth varieties, then you have to use Hironaka's resolution of singularities and so on and so forth. It's quite technical. Okay, it's not obvious. And this is one of the key places. In fact, it is the key place where a uniform numerical criterion is used in Gaussian's proof. If you can get rid of that, you're almost done. Except, so in a neighborhood of the bad set, sure, you find a metric. elsewhere, the current is better behaved, but it's still a very singular object, right? Now, had the Lelong numbers of the current been 0, then we could have approximated this current by smooth things using a very clever gluing procedure of Botsky and Kolodje. Okay? And in fact, Botsky and Kolodje give a counter example when the Lelong number is strictly positive in their paper to their technique, except it's a counter. Botsky and Kolodje, what they prove is roughly, if you have a plurisubharmonic function, I'm lying a little bit, it's a quasi-plurisubharmonic function. But if you have such a beast of 0 Lelong numbers, you can approximate it by smooth functions. It's absolutely correct that if your Lelong numbers are not 0, you cannot approximate by smooth functions. Sure, that is correct. But that is not necessary in Gaussian's proof. You don't need to do any approximation by smooth functions. So he boldly generalized this gluing technique to his case of non-zero Lelong numbers to smoothen theta and glue it to omega prime. When you do this, you lose a little bit of positivity, and hence he needed this theta to lie in omega minus a little bit of positivity. Okay, because you should be allowed to add some positivity, because you lose positivity in this last step. Okay. Alright, so this is roughly Gaussian's proof, but obviously the details are highly technical and clever. So our proof follows a similar strategy, okay? Except one of our key insights is that we avoid the usage of the diagonal that was used in de Maillet-Pont and Gaussian's proof, at the cost of assuming that we have a projective manifold. So at the cost of assuming we have lots of subvarieties, we avoid the use of the diagonal. Please note that this is not just a technicality. We are not avoiding the use of the diagonal because it's difficult to deal with. It's, I mean, if you look at this particular part of Gaussian, this concentration of mass business, we are not sure of how one can do it for the generalized Monge Ampere equation, the analogous result of Gaussian here for the generalized Monge Ampere equation. Okay. In fact, we don't even know if it can be done. Okay, so it's a crucial technical point. It's not just for simplifying our work. Okay, so that's one thing. So assuming Y is an ample divisor, so already that's equivalent to being a projective manifold, the existence of such a divisor, we prove that there is a current theta lying in omega and not in a slightly smaller class, lying in omega, satisfying the cone condition in the sense of Gaussian, and it puts some mass on Y. Okay, we proved this. Now comes the punchline. If you subtract from it del bar of something, then the resulting thing is going to satisfy a better cone condition away from Y. Okay, basically we are getting this sort of a thing except away from an ample divisor. Alright? Okay. So we first assume the uniform numerical criterion and follow Gaussian's proof, and then later on we get rid of it. So we produce omega prime just like Gaussian. One produces an omega prime in the neighborhood of this bad set. Alright, and glue it using Gaussian's technique. Again, it's a little more technical in our case because of Y, because of this ample divisor. We only know that the better cone condition is met outside Y, so there's a small technical Lelong number lemma, but we can do this. Now, if you don't assume the uniform numerical criterion, then it gets very technical. Unfortunately, I can't tell this, I mean, I can't convey our ideas very quickly in this. It's a technical result, but the rough idea is as follows. If you take omega and take omega into 1 plus t, where t is positive, that satisfies the uniform numerical criterion. So we can use our results for the uniform case and then make t go to 0, except that's not good enough to use Gaussian's gluing. So then we have to then we have to do some more work. Basically, the most technical parts of the argument appear when you use this resolution of singularities. That's where you have to do a little bit of perturbation, etc., etc. Okay. But anyway, our key idea is basically this thing. Okay, this is our key point. If one knows this and one knows a technical long number lemma, then one can more or less follow one's nose to try to prove it, except again in the last case one needs to put in a little more effort. Okay, so this is our proof essentially. Alright, so I'll stop here. Thank you very much for listening.